So yeah, here are the equations that you all know and love, right? These are the x and y momentum equations, and basically they are Newton's law, right? Force equals mass times acceleration, or in this case, force per unit mass is acceleration. So on the left we have acceleration, and on the right we have the force, okay? So here is the term that appears when you have a rotating planet, and you think of that as the Coriolis force, okay? So why is it on the left-hand side of the equation? Well, traditionally we put it there because it's not a real force. It doesn't really exist. It's just an artifact of having changed our coordinates. But we put it on the left, and that's convenient because it can be thought of as balancing the pressure gradient force. So here is the real force, the pressure gradient force. And in this blue box, you've got the simplest balance that you can think of. That's geostrophic balance. But as long as you don't include these terms, all these advection terms, these nonlinear terms, can also be included in a higher order balance. It's the kind of balance you need to describe, for example, the difference between a small intense cyclone or a big flat anticyclone, right? You can't do that just by talking about geostrophic balance. You need to include some higher order terms, nonlinear terms. Nonlinearity leads to asymmetry, so that's why those two systems are different in size and intensity. Here's the development, okay? So without this term, you can't do any forecasting, right? Unless your forecast is persistence, right? So this is the key. And if you have that term in there, then you can also consider which other terms you're interested in. So here are the nonlinear terms in orange. Do we keep them or do we not keep them? If you're interested in advection, then you have to keep the advection terms. But it's quite useful and interesting sometimes to just study a developing linear system, and so that will give you wave solutions, and we can go a long way with that as well. Here are the rest of the equations, the primitive equations. So these are the x and y momentum equations, and then we have the vertical momentum equation, which is leading order balance is just a balance between gravity and the vertical gradient of pressure. So that's hydrostatic balance. Then we have a continuity equation, three-dimensional non-divergence. And then we have this equation, which I've put, the density equation. So this describes if you're a parcel of fluid, if you're flowing along, how is your density going to change, right? So this is the substantial derivative of density. And the only thing, this is an oceanographic type viewpoint. So in the ocean, if you're a parcel of water, the only thing that's likely to change your density is diffusion, right? Hard to imagine something else changing the density unless you're in contact with the surface, right? So if you want to think about temperature, if you want to think about the atmosphere, then you'd have to add a thermodynamic equation. That's why I put that in brackets. So you can change the temperature through terms which are on the right-hand side of the equation. So those are the terms, heating and cooling terms, radiative heating, diabatic heating. And then you'd have to add another equation because you've added another variable, right? We've still got density in the equation, we've added temperature, so we need another equation, and that would be the equation of state, P equals rho RT. So if you're dealing with the atmosphere, you need an extra equation. If you're dealing with the ocean, I decided to show the ocean type case here, make it a bit simpler, okay? So have I said everything which is in this list of things to say? If the flow is balanced, it will not develop. If you want to do a prediction, you need the development term. Nonlinear terms are the advection terms. A linear system can still develop. That's the wave solutions. We have 5 variables, okay? So what are our 5 variables? U, V, W, the 3 wind components or current components, and then density and pressure, okay? So we've got 5 variables, we need 5 equations. And there we have 5 equations. We've got 2 prognostic momentum equations, a diagnostic hydrostatic equation, there's no development in that equation, a diagnostic continuity equation, conservation of mass, and a prognostic equation for density, okay? Which might well just be the conservation of density, but it's still a prognostic equation. Okay? Right. So let's start out by considering a balanced situation. If we have no density variations at all, imagine a homogeneous fluid, a fluid which has constant density in all directions. Can we have geostrophic flow? Well, yes, we can, because you can have a change in the height of the surface. So if you have a tilted surface to your fluid, then all throughout the fluid, you'll have horizontal gradients of pressure. So if you have a horizontal pressure gradient, you can accelerate the flow and you can get it into geostrophic balance, right? So you can have a flow in a homogeneous fluid. But it's more interesting when the density starts to vary. So if you have variations of density in the fluid, then you can start talking about the effect of those density variations on the flow field. And that's the simplest balance there would be geostrophic balance in the horizontal, hydrostatic balance in the vertical. This leads to what we call thermal wind balance. And I've done a thermal wind balance derivation here using the Boussinesq approximation, which is that the density only varies a little bit. So here's our geostrophic equation. dP by dx is rho f Vg. Vg is the geostrophic meridional flow. And here's the hydrostatic equation. Okay? So you just cross-differentiate those two equations to give you d squared p by dx dz, and you'll get this equality between these two terms. The Vg by dz is related to d rho by dx. So the vertical gradient of the flow depends on the horizontal gradient of the density. Right? That is thermal wind balance. Now, why am I showing you this? Because I want to show you an example of how you can make things better by changing your vertical coordinate. Okay? So here we've used z as a vertical coordinate, and we've had to use this approximation. So you see, I put rho naught here. That is a kind of reference density. It's something which doesn't change. It's a constant. So that's the Boussinesq approximation that I've used. And so when I've done my dP by dx, I haven't looked at horizontal gradients of density for this. And we have a rho naught here. So is it possible to come to the same conclusion, the same type of thermal wind balance, without making that approximation in a simple way? And it is if we, instead of using z as our vertical coordinate, we use pressure. Okay? So here is a pressure surface in zx space, right? And here's, so P1 here, P2 here. There's a horizontal gradient of pressure. Of course, along this surface there is no change in pressure because it's a pressure surface, right? And so if we want to take this horizontal pressure gradient and express it in pressure coordinates, then it would be the slope of this surface, right? So you can convince yourself from that diagram fairly easily that dP by dx at constant z is minus dP by dz times dz by dx, which is the slope of that surface. And if you do that, well, that's our geostrophic equation. Our hydrostatic equation is unchanged. It's just the vertical pressure gradient. And then you can use those relations to form this, this final result, which is that F over G times dVg by dP, so that's the gradients, the vertical gradient of the geostrophic flow in pressure coordinates, is related to the horizontal gradient on a pressure surface. So it's not the gradient along the pressure surface, it's the horizontal gradient, but measured on the pressure surface, okay? Of this quantity here, 1 over rho, the specific volume. So it's the same. You still have vertical gradient of flow is related to horizontal gradient of density, or something related to density. So that's our thermal wind balance in pressure coordinates. The difference is that we haven't made any approximations here. Right? We haven't, well, we've assumed that it's geostrophically and hydrostatically balanced, but we haven't used any approximations for the density field. Right? And we get to the same conclusion. The other useful or interesting interpretation we can make from this manipulation that we've done, right, is that this is the variation along a pressure surface of the density, right? Now, if the pressure and the density are related, if they're functionally related, so if, imagine a pressure surface and a density surface, if they are parallel, that means that the density doesn't change along the pressure surface, right? In which case, this term would be 0, right? Because there'd be no gradient of density along that pressure surface. That kind of flow is called barotropic flow, okay? That's strictly the definition of barotropic flow, where there is no change of density along a pressure surface, right? And in that case, there's no vertical gradient of the current or of the wind. So barotropic flow, according to this definition, which is the definition of barotropic flow, means that there's no vertical variation in the flow. It's very clearly demonstrated by this little exercise here. Right. So, since I've been talking about the variations of density, let me just go over some of the different levels of approximation that you can use. Right. This is a useful kind of glossary, if you like, for different ways of approximation. So increasing levels of accuracy. We have the homogeneous flow, right, is when there's no variation in density at all. The fluid has the same density everywhere. So that's just like a bucket of water which is spinning around. It's the variations of the free surface which give the variation of the flow. Okay? And so your density is constant. Your pressure doesn't have to be constant. It can vary. It will vary in Z, because as you go down, the pressure will increase. And it can also vary in X and Y and time, because your free surface might be moving around. Okay, but your flow or your horizontal gradients of pressure will not vary with depth. Okay, so your flow is the same all the way down. That's homogeneous flow. Boussinesq flow is the next level up. So you have a reference density and you have a perturbation, okay, which is small compared to the reference density, right? And you can see that it can vary in X, Y, Z, and time. The pressure is a kind of reference pressure, which is only a function of Z, and you'll have perturbations in pressure which are associated with the dynamics. Those horizontal gradients of pressure will belong to this perturbation here. Right? Now, is the Boussinesq approximation a good approximation? How useful is it? Well, I would say for the ocean, it's a very good approximation. I mean, how much does the density vary in the ocean? Water is supposed to be incompressible, right? It's not really incompressible. It's a bit compressible. But what's the density of seawater? It's about 1,025 kilograms per meter cubed, right, near the surface. And if you go down to the bottom of the ocean, it's about 1,040, something like that. So it's denser, but it's not much different. The variations in density, even just to do with compression, are small compared to the actual density. So it's a really excellent approximation in the ocean. And how about the atmosphere? How much does density vary in the atmosphere? Well, what's the density at the surface? It's about 1 kilogram per meter cubed, right? And as you go up through the atmosphere, it gets less and less. So there really are large variations in density in the atmosphere. And yet, the Boussinesq approximation is still useful in the atmosphere, because those variations in density are mainly in the vertical, right? So they don't affect the horizontal gradients of density, and they don't play into the dynamics of the atmosphere. So you can study the atmosphere using the Boussinesq approximation at large scales, and it works. Okay? If you really do need to look at the variation of density with height, then you can use the anelastic approximation, where the reference density is a function of Z and you have a perturbation. That's more for smaller scale, mesoscale type meteorology. And then, so those are our three approximations. Then we have our definition of barotropic. Barotropic is where the density is a function of pressure. And the consequence of that is that there is no vertical variation of the geostrophic flow. Okay? Baroclinic, what does baroclinic mean? It just means it's not barotropic, basically. So you do have variations of density on pressure surfaces, and that with all sorts of interesting consequences. So let's just go over that again. I'll just say this. I think I'll just read this to you. What's written here. So we've seen that in some circumstances the flow is vertically coherent. Depth-independent flow is associated with the barotropic component, also referred to as the external mode. Why is it also called the external mode? It's to do with the fact that it's to do with changes in the level of the free surface, and which are transmitted throughout the depth of the fluid. So it's an external influence on the flow. Barotropic flow can exhibit many phenomena: vortices, Rossby waves, jets, instability. It's a good starting point for a lot of understanding of atmospheric and oceanic dynamics. Particularly, it is the foundation of large-scale ocean circulation theory. Right? All the theories that you did last year about the large-scale ocean were all barotropic. Stommel, Monk, all that. Okay, if you remember that. How about baroclinic? When density surfaces cross pressure surfaces, the flow is baroclinic. The baroclinic component is associated with horizontal temperature gradients, fronts, developing cyclones, ocean eddies on the thermocline. Baroclinic processes are necessary to liberate potential energy and generate circulation. Okay, so the growth of geostrophic systems depends on baroclinic conversions of energy. Baroclinic instability occurs on a preferred scale, which is called the Rossby radius, which we'll be talking about a lot. Okay? And this is important for generating geostrophic turbulence. Okay. Right, a quick word on different ways of dividing the flow, mainly in the atmosphere. Okay? You see I'm moving between the atmosphere and the ocean all the time in this course. This course is designed to be useful for both, right? So, stationary waves. What does an atmospheric scientist mean when he talks about stationary waves? Well, I think he's using the wrong terminology, basically. A stationary wave really is like a wave which has fixed nodes, and it propagates, you know, in situ without, well, it doesn't propagate, it oscillates in situ without propagating. That's a stationary wave. Like in the bath, you know, when you move in the bath and it goes like this. Right? But what a meteorologist means when he says stationary waves is something much simpler. It's just whatever is not the zonal average. Okay, so take a variable, take its zonal average. The variable is the zonal average plus the stationary wave. It's as simple as that. So if you look at this diagram here, this is the 500 millibar height in the wintertime, and if you take the average around the latitude circle and then subtract that average, what's left is this. That's the stationary wave pattern. Okay? The stationary waves are important because there are fluxes in the atmosphere. So if you're interested in the flux of temperature or heat, which is affected by the circulation, right? Then the zonal average of that flux will depend on two things. It will depend on the flux of the zonal average temperature by the zonal average wind. So that is your overturning circulation cells, your Hadley cell, your Ferrel cell, okay? And it'll be the zonal average of the product of the stationary wave wind with the stationary wave temperature. That is the flux affected by zonal non-uniformities and temperature contours being driven by anomalous winds. Okay? Now, both of these things are independent of time, usually. Usually take the average circulation, as I've done here, and decompose it into these two components. And there's another component to the flux which is even more important, and that is the transient part. Okay? So if you then take the average of the flow, the instantaneous flow is equal to that average plus a perturbation, right? And you can do the same kind of decomposition. You can say the average flux is the flux by the average flow, so that's everything up here, okay? Plus this bit, the transient eddy flux. So that is the very important transfer of temperature and momentum which is carried out by these transient systems in the atmosphere and in the ocean, right? Now, another way of looking at that, so yeah, here's a picture which shows the transient flux of temperature. can't even read what the level is. What's the level? 850 millibars. So here are what you call the storm tracks. These two regions, one is in the Atlantic, the West Atlantic, and one is in the West Pacific, where you have the most intense transfer of heat associated with these synoptic transient systems. So if you write down an equation for the development of the temperature, all right, d by dt of the temperature, plus an advection term, v dot grad t, that will be equal to whatever your forcing is minus whatever your dissipation is, okay? But then you can also take the average of that equation, and it'll look like this. It'll say that the flux by the average flow is equal to the average forcing and dissipation, plus another term, which is, put it on the right-hand side here, which is the transient flux. But it's really just part of the flow, but it's often regarded as another type of forcing. It's a kind of thing which balances the mean advection. The transient advection balances the mean advection. Okay? And often look at the atmosphere in that way.